Since the dawn of humanity, we have constantly sought new ways to peer deeper into the heavens. This is the story of one of science's most revolutionary inventions, the telescope. Join us on a journey through time as we explore how these instruments evolved from simple lensed tubes to complex orbital machines that have transformed our understanding of the universe. Did you know that the telescope which revealed Jupiter's moons in the 17th century was less powerful than a modern pair of binoculars? Imagine what the pioneers of astronomy would say if they could see the telescopes we have today. If this voyage through the history of telescopes has piqued your cosmic curiosity, don't stop here. Show your support with a like, share this with your science and astronomy-loving friends, and subscribe to the Exploring the Universe channel. Together, let's continue uncovering the wonders of the universe through the ever more powerful lenses of science. In the earliest days of human civilization, our ancestors gazed at the night sky with nothing but their naked eyes, yet they managed to create extraordinary structures that demonstrated their deep understanding of celestial movements. The magnificent Stonehenge in England stands as a testament to this primitive yet profound astronomical knowledge. Its massive stone pillars were strategically positioned to mark important celestial events, including the summer and winter solstices, revealing how our ancestors used the sky as their calendar. Ancient Egyptian civilization took this understanding further, constructing the Great Pyramids with incredible astronomical precision. Each side of the pyramids was aligned with remarkable accuracy to the four cardinal directions, while specific shafts within the pyramids pointed to important stars in their mythology, such as Sirius and the stars of Orion's belt. Across ancient civilizations, people developed increasingly sophisticated methods of observing the heavens. The invention of the astrolabe in ancient Greece, later refined by Islamic astronomers, revolutionized celestial navigation and timekeeping. This remarkable instrument allowed observers to measure the positions of celestial bodies, determine local time, and even calculate latitude, making it an indispensable tool for both astronomers and navigators. The quadrant, another crucial early astronomical instrument, emerged as a simpler yet effective tool for measuring angular distances between celestial objects and their height above the horizon. These measurements proved vital for creating the first detailed star catalogs and understanding celestial movements. The development of optics marked a crucial turning point in astronomical history. In the 11th century, Arab scholars made groundbreaking contributions to the field of optics. The brilliant physicist Ibn al-Haytham, often called the father of modern optics, wrote comprehensive works on the behavior of light and vision. His Book of Optics, laid the foundation for understanding how lenses work and how we perceive light and color. As knowledge spread to medieval Europe, the craft of lensmaking began to flourish. In Italian city-states and the Low Countries, skilled craftsmen developed techniques for grinding and polishing glass into increasingly precise shapes. These advances in lens crafting, though initially focused on creating spectacles for reading, would later prove crucial for the development of the telescope. Monasteries across Europe became centers of knowledge preservation and advancement, with monks carefully documenting and improving upon ancient optical theories. The combination of theoretical understanding from Arab scholars and practical craftsmanship in European workshops created the perfect conditions for the eventual invention of the telescope, which would forever change our view of the cosmos. This fascinating period of human history shows how our ancestors, armed with nothing but curiosity and ingenuity, laid the groundwork for all future astronomical discoveries. From simple naked-eye observations to the development of sophisticated measuring instruments and the crucial advancement of optics, each step brought us closer to piercing the veil of the cosmic mystery that surrounds us. The dawn of the 17th century ushered in one of humanity's most transformative inventions. In the bustling Dutch town of Middelburg, a skilled spectacle maker named Hans Lippershey made a discovery that would change our understanding of the universe forever. In 1608, while working in his shop, Lippershey noticed that when two lenses were held at a specific distance, distant objects appeared much closer and larger. Lippershey's breakthrough led him to submit a patent application to the States General of the Netherlands. His device, consisting of a convex objective lens and a concave eyepiece lens in a tube, could magnify objects up to 3 times. Although his patent was ultimately denied due to similar claims from other craftsmen, news of this revolutionary instrument spread rapidly across Europe. The real astronomical revolution began when these news reached the ears of an Italian mathematician and natural philosopher, Galileo Galilei. In 1609, having only heard descriptions of the Dutch invention, Galileo set out to create his own improved version. Through meticulous experimentation and superior lens-grinding techniques, he created a telescope that could magnify objects up to 20 times, a remarkable improvement over Lippershey's original design. Galileo's first observations with his telescope were nothing short of extraordinary. On January 7, 1610, he turned his telescope toward Jupiter and discovered 4 bright points of light around the planet. Over several nights of observation, he realized these points were moons orbiting Jupiter, the first concrete evidence that not everything in the cosmos revolved around Earth. These moons, now known as the Galilean satellites, were named Io, Europa, Ganymede, and Callisto. Perhaps even more revolutionary were Galileo's observations of Venus. He discovered that Venus displayed phases similar to our moon, which could only be explained if Venus orbited the Sun rather than Earth. This observation dealt a severe blow to the geocentric model of the universe and provided compelling evidence for Copernicus's heliocentric theory. The telescope's impact on scientific thought was profound and far-reaching. It shattered the ancient belief in the perfection of celestial bodies when Galileo observed mountains and valleys on the moon, spots on the sun, and countless stars in the Milky Way that were invisible to the naked eye. These discoveries fundamentally challenged Aristotelian cosmology, which had dominated Western thought for nearly 2 millennia. The scientific revolution sparked by the telescope extended far beyond astronomy. It demonstrated that human senses could be enhanced by instruments, leading to new ways of conducting scientific investigation. The telescope became a symbol of empirical observation, triumphing over traditional authority and speculation. This new way of understanding the universe through observation and evidence rather than philosophical argument marked a crucial shift in human thought. The telescope helped establish the foundation of modern scientific methodology, where theories must be supported by observable evidence rather than merely logical argument or appeal to authority. The birth of the telescope in the 17th century represents more than just a technological advancement. It marks a fundamental shift in how humans perceive their place in the cosmos. From believing Earth was the center of a perfect, unchanging universe, we began to understand our true place in a vast, dynamic cosmos. This revolutionary instrument not only extended our vision into the heavens, but also expanded the horizons of human knowledge and understanding in ways that continue to resonate today. The age of giant refracting telescopes represents one of astronomy's most ambitious periods, marking humanity's first serious attempt to build instruments of truly magnificent proportions. A refracting telescope's principle is elegantly simple. Light enters through a large objective lens at one end, travels down a long tube, and is focused through an eyepiece lens at the other end, creating a magnified image of distant celestial objects. In a refracting telescope, the objective lens serves as the primary light-gathering element. The larger this lens, the more light it can collect, and consequently, the fainter the objects it can detect. This fundamental principle drove astronomers and craftsmen to pursue ever larger objective lenses, leading to an era of remarkable technological achievement and scientific discovery. However, these early astronomers faced significant challenges. Perhaps the most vexing was chromatic aberration, a phenomenon where different wavelengths of light focus at slightly different points, creating colored fringes around observed objects. This optical distortion occurred because traditional lenses acted like prisms, splitting white light into its component colors. The effect was particularly pronounced in early telescopes, often rendering detailed observations difficult or impossible. A breakthrough came with the development of achromatic lenses, which combined different types of glass with varying refractive properties. These compound lenses significantly reduced chromatic aberration, though never eliminated it entirely. Chester Moore Hall first developed this technology in the 1730s, and John Dollond later patented and popularized it in 1758. The size limitations of refracting telescopes presented another formidable challenge. As lenses grew larger, they became increasingly difficult to manufacture without defects. Moreover, large lenses tended to sag under their own weight, distorting the image. The glass needed to be thick enough to maintain its shape, but thin enough to allow light transmission, creating an engineering paradox that ultimately limited the maximum practical size of refracting telescopes. The Great Refractor of the Paris Observatory, completed in 1671, represented an early triumph in large telescope construction. This instrument, with its 38-foot focal length and 12-inch objective lens, was built under the direction of Giovanni Domenico Cassini. Using this telescope, Cassini discovered 4 of Saturn's moons and the gap in Saturn's rings that now bears his name. The Paris refractor demonstrated the potential of large telescopes and inspired a 2-century quest for even larger instruments. The pinnacle of refracting telescope technology came with the Yerkes Observatory's Great Refractor in 1897. This magnificent instrument, featuring a 40-inch diameter objective lens and a tube 63 feet long, remains the largest operational refracting telescope ever built. The creation of its massive lenses was a masterwork of optical engineering by Alvin Clark and Sons, requiring extreme precision in grinding and polishing 2 discs of glass weighing 500 pounds each. The Yerkes refractor represented both the triumph and the practical limits of refracting telescope technology. Its construction required solving numerous engineering challenges, from supporting the massive tube without distortion to maintaining perfect alignment of the optical elements. The telescope's mount, a marvel of late 19th century engineering, allows the enormous instrument to track celestial objects with remarkable precision. Despite its impressive size, the Yerkes refractor marked the end of an era. The practical limitations of lens size, combined with the emergence of reflecting telescope technology, meant that no larger refractors would ever be built. Nevertheless, the Yerkes telescope remains operational today, a testament to the craftsmanship of its builders and a bridge between classical and modern astronomy. These giant refractors contributed significantly to our understanding of the universe. They enabled detailed studies of planets, discovered numerous double stars, and helped measure stellar parallax. Their legacy lives on not only in the discoveries they made, but also in the engineering principles developed to build them, which continue to influence modern telescope design. The era of giant refractors represents a unique period in astronomical history when the limits of classical optical technology were pushed to their absolute maximum. While modern telescopes have far surpassed their light-gathering power, these magnificent instruments remain symbols of human ingenuity and our eternal quest to understand the cosmos. The reflecting telescope marked a revolutionary turning point in astronomical observation, fundamentally changing how we peer into the depths of space. Unlike its refracting predecessors, this ingenious invention used mirrors rather than lenses to gather and focus light, opening new possibilities for astronomical discovery. At the heart of a reflecting telescope lies a beautifully simple principle. A large curved primary mirror collects incoming light and reflects it to a focus point, where a smaller secondary mirror directs the light to an eyepiece. This elegant design would prove to be one of astronomy's most significant innovations, offering solutions to problems that had long plagued refracting telescopes. In 1668, a young Isaac Newton unveiled his groundbreaking creation, the first practical reflecting telescope. Newton's design featured a 6-inch-long tube, housing a primary mirror made of polished metal. Though modest in size, this instrument demonstrated the immense potential of reflector technology. Newton's innovative design used a small flat secondary mirror set at a 45-degree angle to direct light to an eyepiece on the telescope's side, a configuration that would later become known as the Newtonian reflector. The advantages of reflecting telescopes over their refracting counterparts were substantial and immediately apparent. Perhaps most significantly, reflectors completely eliminated the persistent problem of chromatic aberration, the rainbow-like color distortion that had plagued refracting telescopes. Since mirrors reflect all wavelengths of light to the same focal point, the images produced were free from these troublesome color fringes. Moreover, reflecting telescopes offered a practical pathway to building substantially larger instruments. Unlike lenses, mirrors could be supported from behind, eliminating the sagging problems that limited refractor size. This advantage would prove crucial in pushing the boundaries of astronomical observation. The true potential of reflecting telescope technology reached its 19th century pinnacle with the construction of the legendary Leviathan of Parsonstown in 1845. Built by the Earl of Ross in Ireland, this magnificent instrument featured a massive 6-foot diameter primary mirror, making it the largest telescope in the world for over 7 decades. The telescope's tube was so enormous that it required the construction of massive walls on either side to support its movement. The Leviathan's unprecedented light-gathering power enabled groundbreaking observations. Lord Ross used it to discover the spiral structure of what we now know are galaxies, initially termed spiral nebulae. This revelation fundamentally changed our understanding of the universe's structure. The telescope also allowed astronomers to resolve numerous nebulae into distinct star clusters, providing crucial insights into the nature of these cosmic objects. The success of the Leviathan of Parsonstown demonstrated the immense potential of large reflecting telescopes, paving the way for the modern era of giant observatory telescopes. Its legacy lives on in the massive reflecting telescopes that dominate modern astronomy, from the historic Mount Palomar Observatory to today's very large telescope array. The reflecting telescope revolution represents one of humanity's greatest technological achievements, transforming our ability to study the cosmos. From Newton's modest 6-inch reflector to the towering Leviathan of Parsonstown, each advancement brought us closer to understanding our place in the vast cosmic ocean. Isn't it remarkable how human ingenuity has taken us so far? If you're enjoying this journey through telescope history, show your support with a like. Don't forget to subscribe for more amazing content about the history of science and astronomy. The 20th century ushered in a golden age of astronomical discovery, marked by the construction of increasingly powerful telescopes that would forever change our understanding of the cosmos. This era saw the birth of modern observatories that would reveal the true nature and scope of our universe. The story begins with the magnificent Hooker telescope at Mount Wilson Observatory, which first saw light in 1917. This 100-inch reflecting telescope represented an extraordinary leap forward in astronomical capability. Perched high in the mountains above Los Angeles, the telescope's location was chosen for its stellar atmospheric conditions and relative freedom from light pollution. The Hooker telescope's most famous user was Edwin Hubble, whose observations would revolutionize our understanding of the universe. Using this powerful instrument, Hubble made two transformative discoveries. First, in 1924, he proved that the Andromeda Nebula was actually a galaxy far beyond our Milky Way, demonstrating that the universe was vastly larger than previously imagined. Then, in 1929, he discovered what we now call Hubble's law, the observation that distant galaxies are moving away from us at speeds proportional to their distance, providing the first evidence of the expanding universe. In 1948, astronomy took another giant leap forward with the completion of the Hale telescope at Palomar Observatory. With its massive 200-inch, 5-meter, mirror, the Hale telescope reigned as the world's largest telescope for nearly half a century. The construction of its mirror was an extraordinary feat of engineering. The massive disk of glass took 11 years to cast, cool, and polish to the required precision. The Hale telescope dominated astronomical research for decades, enabling countless groundbreaking discoveries. Its unprecedented light-gathering power allowed astronomers to peer deeper into space than ever before, revealing countless new galaxies, quasars, and other celestial phenomena. The telescope's observations helped establish the cosmic distance scale, map the structure of the universe, and advance our understanding of stellar evolution. As the century progressed, technological innovations revolutionized how these great telescopes operated. The introduction of computerized equatorial mounts transformed telescope control. These sophisticated systems could automatically track celestial objects as they moved across the sky, compensating for Earth's rotation with unprecedented precision. This automation allowed astronomers to spend more time observing and less time manually guiding their telescopes. Perhaps the most significant technological breakthrough was the development of adaptive optics. This revolutionary technology uses computer-controlled deformable mirrors to compensate for atmospheric turbulence, the phenomenon that causes stars to twinkle. By measuring atmospheric distortion hundreds of times per second and adjusting the mirror shape accordingly, adaptive optics systems can produce images nearly as sharp as those taken from space. The system works by using a bright reference star or an artificial laser guide star to measure atmospheric distortion. The computer then calculates the necessary corrections and applies them by flexing the deformable mirror, effectively canceling out the atmospheric blur. This technology has given ground-based telescopes capabilities approaching those of space-based observatories for many types of observations. These technological advances weren't limited to the telescopes themselves. The introduction of electronic detectors, particularly charge-coupled devices, replaced photographic plates, dramatically improving the efficiency and sensitivity of astronomical observations. Digital imaging and processing techniques allowed astronomers to extract more information from their observations than ever before. The great observatories of the 20th century represented more than just technological achievements. They were temples of discovery that fundamentally changed our cosmic perspective. From proving the existence of other galaxies to revealing the expanding universe, these magnificent instruments opened our eyes to the true nature of the cosmos. Through their eyepieces, we learned that we live in an expanding universe populated by billions of galaxies, each containing billions of stars. We discovered exotic objects like quasars and pulsars, mapped the large-scale structure of the cosmos, and began to understand the life cycles of stars and galaxies. The telescopes of this era truly ushered in the modern age of astronomy, laying the groundwork for the even more powerful instruments that would follow. The story of radio astronomy begins in an unlikely place, the Bell Telephone Laboratories in New Jersey. In 1933, a young engineer named Carl Jansky made a discovery that would open an entirely new way of observing the cosmos. While investigating sources of static that might interfere with transatlantic radio communications, Jansky detected a steady hiss of radio waves coming from the constellation Sagittarius in the direction of the Milky Way's center. This serendipitous discovery marked humanity's first detection of radio waves from space, revealing that the universe had far more to tell us than what we could see with our eyes. Jansky's pioneering work demonstrated that celestial objects emit not only visible light, but also radio waves, which could penetrate dust clouds that block optical observations. This revelation would prove revolutionary, as radio astronomy would soon allow us to peer through the cosmic dust that obscures much of our galaxy, revealing previously hidden wonders of the universe. The field of radio astronomy truly came into its own with the construction of massive radio telescopes. The most iconic among these was the Arecibo Observatory in Puerto Rico, completed in 1963. Built into a natural sinkhole, its enormous 1,000-foot diameter reflector dish made it the world's largest single-aperture telescope for over 5 decades. The scale of Arecibo was staggering. Its collecting area spanned nearly 20 acres, allowing it to detect incredibly faint radio signals from the depths of space. Arecibo's contributions to astronomy were profound. It played a crucial role in determining the rotation rate of Mercury, discovered the first binary pulsar system, which provided the first indirect evidence for gravitational waves, and sent humanity's most powerful broadcast to potential extraterrestrial civilizations, the famous Arecibo message of 1974. The telescope also served as Earth's primary instrument for planetary radar studies, helping map the surfaces of Venus and Mercury and tracking potentially hazardous near-Earth asteroids. Another revolutionary development in radio astronomy came with the Very Large Array in New Mexico, which began operations in 1980. The VLA takes a different approach to radio astronomy, consisting of 27 individual radio antennas arranged in a Y-shaped configuration. Each antenna is 82 feet in diameter, and they work together as an interferometer, effectively creating a telescope with the resolution of a single dish up to 22 miles across. This innovative design allows the VLA to produce detailed radio images with resolution comparable to the best optical telescopes. The facility can be reconfigured by moving the antennas along railroad tracks, allowing astronomers to adjust the array's resolution and sensitivity for different types of observations. This flexibility has made the VLA one of the most productive astronomical instruments ever built. The impact of radio astronomy on our understanding of the universe has been nothing short of revolutionary. One of its most dramatic discoveries came in 1967, when Jocelyn Bell Burnell and her thesis advisor Anthony Hewish detected the first pulsar, a rapidly rotating neutron star emitting regular pulses of radio waves. This discovery provided the first observational evidence for the existence of neutron stars, which until then had been purely theoretical objects. Perhaps radio astronomy's greatest contribution to our understanding of the cosmos came with the discovery and detailed study of the cosmic microwave background radiation. First detected by Arno Penzias and Robert Wilson in 1964, the CMB represents the afterglow of the Big Bang itself. This faint radio signal, coming uniformly from all directions in space, provides the strongest evidence for the Big Bang theory and has become our primary window into the early universe. Radio astronomy has revealed phenomena that would have remained forever invisible to optical telescopes. It has shown us the violent jets emanating from supermassive black holes at the centers of galaxies, mapped the distribution of hydrogen gas throughout the Milky Way, and detected complex organic molecules in interstellar space. The technique has even been crucial in the search for extraterrestrial intelligence, monitoring the sky for potential artificial signals from other civilizations. Modern radio telescopes continue to push the boundaries of our knowledge. Networks of radio telescopes working together have produced the first images of a black hole's event horizon, while new facilities like the Square Kilometre Array promise to revolutionize our understanding of the early universe, cosmic magnetism, and the nature of dark energy. The development of radio astronomy reminds us that there's far more to the universe than meets the eye. By expanding our view beyond visible light, we've uncovered phenomena that would have been impossible to detect otherwise. From pulsars to the cosmic microwave background, radio telescopes have revealed a universe far more dynamic and mysterious than anyone could have imagined when Carl Jansky first pointed his antenna at the sky. The launch of space-based telescopes marked a watershed moment in astronomical history, freeing observers from the limitations of Earth's atmosphere and opening up entirely new views of the cosmos. This revolutionary approach to astronomy has transformed our understanding of the universe in ways that ground-based observers could only dream of. Operating telescopes in space offers several crucial advantages. Free from atmospheric interference, space telescopes can observe celestial objects with unprecedented clarity. Earth's atmosphere blocks most wavelengths of light from reaching the ground, but space-based instruments can detect the full spectrum of electromagnetic radiation, from gamma rays to infrared. Furthermore, space telescopes can observe continuously without interference from weather or the day-night cycle. The crown jewel of space astronomy, the Hubble Space Telescope, HST, rocketed into orbit in 1990. Despite initial setbacks with its primary mirror, which required a dramatic space shuttle repair mission in 1993, Hubble has become arguably the most important scientific instrument ever built. With its 2.4-meter mirror and suite of sophisticated instruments, Hubble has peered deeper into space and time than any telescope before it. Hubble's contributions to astronomy have been nothing short of revolutionary. Its observations help determine the age of the universe with unprecedented precision, approximately 13.8 billion years. The telescope's deep field observations, showing thousands of galaxies in what appeared to be empty patches of sky, fundamentally changed our perspective on the scale of the cosmos. These images revealed that the observable universe contains at least 100 billion galaxies, each home to billions of stars. The Space Telescope provided crucial evidence for the existence of supermassive black holes at the centers of galaxies, showing that these mysterious objects are not rare oddities, but fundamental components of galactic evolution. Hubble's observations of distant supernovae also contributed to the discovery of dark energy, the mysterious force accelerating the universe's expansion, a discovery that would earn the 2011 Nobel Prize in Physics. Beyond Hubble, a fleet of specialized space telescopes has revolutionized our view of the cosmos across the electromagnetic spectrum. The Chandra X-ray Observatory, launched in 1999, revealed the violent, high-energy universe invisible to optical telescopes. Chandra's observations have shown us the aftermath of supernova explosions, the hot gas in galaxy clusters, and the X-ray emissions from material falling into black holes. The Spitzer Space Telescope, operating in the infrared spectrum from 2003 to 2020, pierced through cosmic dust clouds to reveal stellar nurseries where new stars are born. Its ability to detect heat radiation made it particularly effective at studying cool objects like brown dwarfs, exoplanets, and distant galaxies whose light has been stretched to infrared wavelengths by the expansion of the universe. The Kepler Space Telescope, launched in 2009, revolutionized our understanding of planetary systems. During its 9-year mission, Kepler monitored over 530,000 stars, discovering thousands of exoplanets. This wealth of data transformed our view of planetary systems, revealing that planets are common throughout the galaxy and exist in configurations far more diverse than we had imagined. These space telescopes have worked together to provide a comprehensive view of cosmic phenomena. For example, when astronomers observe the collision of two neutron stars, Hubble might capture the visible light, Chandra the X-rays, and Spitzer the infrared afterglow, each telescope revealing different aspects of the same event. The success of space telescopes has inspired increasingly ambitious projects. The James Webb Space Telescope, with its massive 6.5-meter mirror, promises to peer even deeper into space and time, potentially revealing the first galaxies that formed after the Big Bang. Future missions will search for biosignatures in exoplanet atmospheres, study the nature of dark matter and dark energy, and perhaps even discover signs of life beyond Earth. The Space Telescope revolution has fundamentally changed not just what we know about the universe, but how we study it. These orbital observatories have revealed a cosmos more dynamic, violent, and beautiful than anyone imagined. From the birth of stars to the death of galaxies, from the first moments after the Big Bang to the current acceleration of cosmic expansion, space telescopes have given us front-row seats to the greatest show in existence. The legacy of space telescopes extends beyond their scientific achievements. The stunning images they produce, particularly from Hubble, have captured the public imagination and brought the wonders of the cosmos into our everyday lives. These pictures have become cultural touchstones, reminding us of our place in the vast cosmic arena and inspiring new generations to explore the mysteries of space. While space telescopes have revolutionized astronomy, ground-based observatories have undergone their own remarkable evolution, achieving capabilities that rival and sometimes surpass their orbital counterparts. Modern ground-based telescopes combine massive light-gathering power with cutting-edge technology to push the boundaries of astronomical observation. The Very Large Telescope in Chile's Atacama Desert stands as a testament to modern astronomical engineering. Operated by the European Southern Observatory, the VLT consists of 4 main telescopes, each with a mirror 8.2 meters in diameter. These behemoths, named Untu, Kian, Melipal, and Yepen, words from the indigenous Mapuche language, can work individually or combine their light through interferometry. Located at an altitude of 2,635 meters on Cerro Paranal, the VLT benefits from some of Earth's clearest skies. The Atacama Desert's extreme aridity and minimal atmospheric turbulence create nearly perfect observing conditions. The facility's location in the southern hemisphere also provides unique views of the galactic center and the Magellanic Clouds, our nearest galactic neighbors. The W.M. Keck Observatory, perched atop Mauna Kea in Hawaii at 4,145 meters, houses 2 of the world's most powerful telescopes. Each Keck telescope features a revolutionary primary mirror design composed of 36 hexagonal segments that work together as a single 10-meter reflecting surface. This segmented design solved the significant engineering challenges of creating and supporting such large mirrors, paving the way for even larger telescopes. These modern observatories employ 2 game-changing technologies that dramatically enhance their capabilities: interferometry and extreme adaptive optics. Interferometry allows multiple telescopes to work together, effectively creating a virtual telescope with a diameter equal to the distance between the individual instruments. The VLT's interferometric mode can combine light from its 4 main telescopes and 4 auxiliary 1.8-meter telescopes, achieving the resolving power of a telescope up to 200 meters in diameter. This technique has enabled unprecedented observations of celestial objects. For instance, interferometric observations have allowed astronomers to track stars orbiting the supermassive black hole at our galaxy's center, providing compelling evidence for its existence and mass. The technique has also revealed details of planet-forming disks around young stars and measured the sizes of distant stars. Extreme adaptive optics represents another leap forward in observational capability. While earlier adaptive optic systems made hundreds of corrections per second to compensate for atmospheric turbulence, extreme adaptive optics makes thousands of corrections using deformable mirrors with thousands of actuators. Systems like the VLT Sphere instrument can achieve image clarity that rivals space-based telescopes. These advanced adaptive optics systems have proven particularly valuable for exoplanet research. They can reduce the blinding glare of bright stars, allowing astronomers to directly image planets orbiting other stars. The first-ever direct images of exoplanets were captured using adaptive optics on the Keck and VLT telescopes. Modern ground-based telescopes also leverage sophisticated instruments that can analyze light in various ways. Spectrographs break light into its component wavelengths, revealing information about celestial objects' chemical composition, temperature, and motion. Multi-object spectrographs can observe hundreds of objects simultaneously, enabling large-scale surveys of galaxies and stars. The success of these observatories has inspired even more ambitious projects. The extremely large telescope, under construction in Chile, will feature a primary mirror 39.3 meters in diameter. This massive instrument will collect 13 times more light than the largest existing optical telescopes and produce images 16 times sharper than the Hubble Space Telescope. The Giant Magellan Telescope and 30-meter telescope are also under development, promising to push observational astronomy to new limits. These telescopes will be able to study the atmospheres of exoplanets, probe the nature of dark matter and dark energy, and perhaps even detect signs of life on other worlds. Modern ground-based telescopes demonstrate that both Earth-bound and space-based observations have crucial roles to play in astronomy. While space telescopes can observe wavelengths blocked by Earth's atmosphere, ground-based telescopes can be built much larger, collect more light, and be upgraded more easily. The combination of these complementary approaches has ushered in a golden age of astronomical discovery, with each new instrument revealing more of our universe's secrets. The advent of these powerful instruments has transformed astronomy from a science of passive observation to one of active investigation. Whether studying the birth of planets, the death of stars, or the evolution of galaxies, modern ground-based telescopes continue to expand our cosmic horizons, reminding us that there is always more to discover in the vast expanse above. The field of astronomy stands on the brink of a new era, with revolutionary instruments and techniques promising to transform our understanding of the cosmos. Leading this new wave of discovery is the James Webb Space Telescope, launched in December 2021, which represents the most ambitious and sophisticated space observatory ever constructed. The James Webb Space Telescope, positioned approximately 1.5 million kilometers from Earth at the L2 Lagrange point, features a 6.5-meter primary mirror composed of 18 hexagonal segments. Operating primarily in the infrared spectrum, JWST can peer through cosmic dust clouds that obscure visible light, revealing previously hidden phenomena. Its infrared capabilities also allow it to observe some of the most distant objects in the universe, whose light has been stretched to infrared wavelengths by cosmic expansion. JWST's potential for studying exoplanet atmospheres is particularly exciting. Its powerful spectroscopic instruments can analyze the light passing through or reflecting off exoplanet atmospheres, potentially detecting biosignatures, chemical signatures that might indicate the presence of life. The telescope can also study protoplanetary disks around young stars, helping us understand how planetary systems form and evolve. On the ground, a new generation of extremely large telescopes is taking shape. The European Southern Observatory's Extremely Large Telescope, under construction in Chile's Atacama Desert, will feature an astounding 39.3-meter primary mirror composed of 798 hexagonal segments. When completed, it will be the world's largest optical/near-infrared telescope, collecting more light than all existing 8 to 10-meter telescopes combined. The YELT's unprecedented light-gathering power and resolution will enable groundbreaking science across many fields. It will be able to study the first galaxies formed after the Big Bang, directly image rocky exoplanets, and probe the nature of dark matter and dark energy. Its adaptive optics system will achieve image quality superior to space-based telescopes in some wavelengths. The 30-meter telescope, planned for construction atop Mauna Kea in Hawaii, represents another leap forward in telescope technology. With its 30-meter primary mirror, the TMT will provide unprecedented views of everything from objects in our solar system to the most distant galaxies. Its location in the northern hemisphere will complement the YELT's southern hemisphere views, providing complete coverage of the celestial sphere. One of the most promising developments in modern astronomy is the emergence of global telescope networks. By coordinating observations across multiple telescopes worldwide, astronomers can achieve continuous coverage of transient events and unprecedented detail in their observations. The Event Horizon Telescope, which produced the first image of a black hole, demonstrates the power of this approach. Looking further into the future, the possibility of lunar observatories presents exciting opportunities. The Moon's airless environment, stable platform, and dark skies during lunar night make it an ideal location for telescopes. The far side of the Moon, perpetually shielded from Earth's radio interference, could host sensitive radio telescopes capable of detecting extremely faint signals from the early universe. Several concepts for lunar observatories are under consideration. These include liquid mirror telescopes that could be constructed using materials extracted from lunar soil, and radio telescope arrays that could be deployed across the lunar far side. Such facilities could provide unprecedented views of the cosmos without the limitations imposed by Earth's atmosphere or ionosphere. The future of astronomical observation will likely involve a synergy between various types of instruments. Space-based telescopes will continue to provide unobstructed views across the electromagnetic spectrum, while ground-based giants will leverage their massive light-gathering power and sophisticated instruments. Lunar observatories might eventually complement both, offering unique capabilities unavailable elsewhere. New technologies will also play a crucial role. Artificial intelligence and machine learning are already transforming how astronomers analyze data, and these tools will become even more important as new telescopes generate unprecedented volumes of information. Advanced materials and manufacturing techniques may enable novel telescope designs, while quantum sensors could provide revolutionary new ways to detect and measure light. The next decade promises particularly exciting developments in several key areas. The search for biosignatures on exoplanets, understanding the nature of dark matter and dark energy, probing the earliest moments of the universe, studying gravitational waves with both ground and space-based detectors, investigating the possibility of extraterrestrial intelligence with more sophisticated tools. These future observatories will not only answer existing questions, but likely reveal new mysteries we haven't yet imagined. The history of astronomy shows that each advance in observational capability has led to unexpected discoveries, and there's no reason to expect the future will be any different. As we look to this future, it's clear that astronomy is entering a golden age of discovery. The combination of new technologies, larger telescopes, and novel observing strategies promises to revolutionize our understanding of the cosmos. From the search for life on other worlds to unraveling the mysteries of dark energy, the next generation of astronomical instruments will help humanity push the boundaries of knowledge further than ever before. The development of telescopes has profoundly transformed not only our scientific understanding of the universe, but also our cultural perspective and philosophical outlook on humanity's place in the cosmos. This revolutionary instrument has repeatedly challenged our assumptions and expanded our horizons, leading to discoveries that have fundamentally altered our worldview. The telescope's impact on our understanding of the cosmos has been revolutionary from its very beginning. Galileo's first telescopic observations in 1609 immediately challenged the prevailing Earth-centered model of the universe. Since then, each advancement in telescope technology has revealed new layers of cosmic complexity, continuously expanding our understanding of the universe's scale and nature. Perhaps the most dramatic transformation has been our growing awareness of the universe's true size. From believing Earth was the center of a relatively small cosmos, we now know we inhabit a modest planet orbiting an ordinary star in a galaxy of hundreds of billions of stars, which is itself one of hundreds of billions of galaxies in the observable universe. The expansion of the universe, first observed by Edwin Hubble using the Mount Wilson telescope in the 1920s, ranks among the most profound discoveries in scientific history. By measuring the redshift of distant galaxies, Hubble demonstrated that the universe is not static but expanding, leading to the development of the Big Bang theory and modern cosmology. This discovery fundamentally changed our understanding of the universe's origin and evolution. The discovery of exoplanets represents another revolutionary breakthrough enabled by telescopic observations. Since the first confirmed detection in 1992, thousands of planets around other stars have been discovered, dramatically changing our perspective on planetary systems and the possibility of life elsewhere in the universe. These discoveries have shown that planetary systems are common and diverse, suggesting that Earth-like worlds might be more numerous than previously thought. The investigation of dark matter and dark energy stands as one of the most intriguing contributions of modern telescopic astronomy. Through observations of galactic rotation, gravitational lensing, and the cosmic microwave background, telescopes have revealed that ordinary matter comprises only about 5% of the universe's content. The remaining 95% consists of mysterious dark matter and dark energy, whose nature remains one of science's greatest unsolved mysteries. Telescopic images have profoundly influenced cultural and artistic expression. The iconic Pillars of Creation photograph from the Hubble Space Telescope, showing stellar nurseries in the Eagle Nebula, has inspired countless artistic works and become a symbol of cosmic beauty. Similarly, images of spiral galaxies, nebulae, and other celestial objects have influenced visual arts, architecture, and design. The telescope's impact extends into literature and popular culture. Science fiction writers have drawn inspiration from telescopic discoveries to create compelling visions of future space exploration and extraterrestrial life. Movies and television shows frequently feature telescopic imagery and astronomical discoveries as plot elements or visual backdrop. Telescopes have democratized astronomy in unprecedented ways. Amateur astronomers can now access sophisticated equipment that would have been unimaginable a few decades ago. Online access to professional telescope data and images has allowed citizen scientists to participate in astronomical research, leading to numerous discoveries. The public's engagement with astronomical discoveries has helped foster scientific literacy and critical thinking. Telescope observations have provided concrete evidence for abstract scientific concepts, making them more accessible to the general public. This has contributed to a broader understanding of scientific methodology and the nature of scientific inquiry. Telescopic discoveries have repeatedly forced us to confront our place in the cosmos. The revelation that Earth is not unique or central to the universe has profound philosophical implications, challenging anthropocentric worldviews and religious doctrines. The discovery of countless galaxies and potentially habitable worlds raises questions about our cosmic significance and the possibility of extraterrestrial life. The development of telescopes has driven technological innovation in numerous fields. Advances in optics, materials science, and digital imaging developed for telescopes have found applications in medicine, industry, and consumer technology. The space telescope industry has spawned numerous spin-off technologies, from improved surgical tools to enhanced digital camera sensors. As new telescopes come online, their potential impact on science and society continues to grow. The James Webb Space Telescope's ability to study exoplanet atmospheres could lead to the first detection of biosignatures on other worlds, potentially answering one of humanity's oldest questions about life beyond Earth. Future extremely large telescopes might help resolve the nature of dark matter and dark energy, fundamentally changing our understanding of physics. The social impact of future discoveries could be equally profound. The potential detection of extraterrestrial life, even in microbial form, would have enormous philosophical, religious, and cultural implications. Similarly, detailed studies of potentially habitable exoplanets might influence our perspective on environmental conservation and humanity's long-term future. Perhaps the telescope's most lasting impact has been its role in inspiring wonder and curiosity about the natural world. Telescope images have given humanity a shared perspective on our cosmic environment, contributing to what astronauts call the overview effect, a profound shift in awareness of Earth's place in the larger cosmos. This perspective has influenced environmental consciousness, highlighting Earth's uniqueness and fragility. It has also inspired generations of scientists, engineers, and explorers, driving technological progress and scientific discovery across multiple fields. The telescope stands as one of humanity's most transformative inventions, not just as a scientific instrument, but as a tool that has fundamentally altered our understanding of reality and our place within it. As we continue to develop more powerful telescopes, their impact on science, society, and human consciousness will undoubtedly continue to grow. Throughout this remarkable journey through the history of telescopes, we've witnessed humanity's relentless pursuit of cosmic understanding. From Galileo's modest instrument that first revealed Jupiter's moons to today's space-based observatories peering into the depths of the universe, telescopes have served as humanity's cosmic eyes, continuously pushing the boundaries of our knowledge. Each technological leap in telescope development has brought transformative discoveries. Galileo's observations challenged the geocentric worldview. The giant refractors of the 18th and 19th centuries revealed the intricate details of our solar system. The revolutionary reflecting telescopes opened new windows into deep space, while radio telescopes unveiled invisible cosmic phenomena. Space telescopes like Hubble have shown us the universe with unprecedented clarity, fundamentally changing our understanding of cosmic evolution, galaxy formation, and our place in the cosmos. As we stand on the cusp of a new era in astronomical observation, with instruments like the James Webb Space Telescope and upcoming ground-based giants like the ELT, we can only imagine the discoveries that await. These powerful tools will probe the atmospheres of distant exoplanets, study the first galaxies formed after the Big Bang, and perhaps help us answer one of humanity's oldest questions. Are we alone in the universe? The story of telescopes is more than a tale of technological progress. It's a testament to human ingenuity, curiosity, and our unwavering desire to explore the unknown. Each generation of astronomers has built upon the achievements of their predecessors, developing increasingly sophisticated instruments to peer deeper into the cosmic mystery. Has this cosmic journey through telescope history ignited your astronomical curiosity? Don't let your exploration end here. Show your support by hitting that like button, and share this video with your fellow science and astronomy enthusiasts. Subscribe to the Exploring the Universe channel to join us on more fascinating adventures through space and time. By subscribing, you'll be part of a community dedicated to unraveling the mysteries of the cosmos. We'll continue to explore groundbreaking discoveries, cutting-edge space technology, and the incredible instruments that allow us to study our vast universe. Don't forget to ring that notification bell to stay updated on our latest uploads. Leave a comment below sharing your thoughts on this incredible journey from Galileo's simple telescope to today's space observatories. What aspect of telescope history fascinated you the most? Until our next stellar adventure, viewed through the ever more powerful lenses of science, keep looking up and wondering about the cosmic mysteries that await discovery. Together, let's continue this extraordinary journey of exploration and discovery that began with a simple tube and two pieces of glass over 400 years ago.